Okay, so good morning to everyone. So today we are going to hear from Sergio and Hernandez-Cuenca on replica wormholes.
All right, well, hello everyone. Thank you very much for the invitation to be here. It's super good to be melting here with you. I bring you a hot topic for hot ferns, replica wormholes. I'll be telling you a bit of a general machinery for dealing with replica wormholes, for computing, generating functionals in quantum gravity, and some general tools for two-dimensional cases like JT. And then I'll explain a tale of two saddles in JT gravity, where these two saddles are basically disconnected and connected phases as usual. So in the introduction, I'll review some of the ideas about introducing connected topologies in the gravitational path integral and how these have taught us a lot of lessons about the page curve and how to compute information quantities in quantum gravity. Then I'll cook up a recipe that I'm calling the chef recipe because of, well, our initials. And that chef recipe will have two components. One of them is Lukowitz Malacina, and then it will have also a pinch of Parisi, which I guess is appropriate since we're in Italy. Then I'll explain a general toolkit in two-dimensional gravity for constructing geometries for replica wormholes. And with all the machinery, I'll then jump into JT and construct saddles in classical JT by introducing classical sources. In the discussion, I'll summarize and leave you with some open questions that remain. And well, I should have said, this is work in progress to appear maybe next month with Ben Chandrasekharan, Netta Engelhardt, and Sebastian Pichetti. Right, so let me begin with this powerful and mysterious object in quantum gravity, which is the Euclidean gravitational path integral. We usually write it somewhat formally as some integral over manifolds and metrics subject to certain manifold boundary condition. Here the manifolds are M with conformal boundary, some manifold B. I'm integrating over metrics weighted by the Euclidean action, or rather e to the minus I. And so what defines the gravitational path integral is these manifold boundary conditions. This is a rather formal object. In general, we cannot make sense of it. We don't have a sensible measure over metrics or manifolds, but we can make sense of it semi-classically by summing over semi-classical saddle points, or in low-dimensional models like JT gravity, where we do have some very nice control over this, like in the story by Satch, Henker, and Stanford, where you can actually sum over all the topologies and get a very nice dual to double matrix model, double scale matrix model. Okay, so in general, the rules we follow, suppose we have some boundary manifold that is just a circle. We're instructed to integrate over all bulk manifolds that asymptote to such a circle. So the obvious geometry that we can begin considering is just this. But we should also sum over all possible genera. So a disk with a hole, disk with two holes, and so on and so forth. Now the interesting thing happens when we consider boundary manifolds that consist of multiple connected components, not just one. So what happens then is that the gravitational path integral is able to, or wants to integrate over manifolds that are connected, even though the boundary is not. And so we would have the obvious contribution of just three disks in the case in which we have three circles, but we would also consider situations where we have a connected wormhole that joins all three boundaries. We can also have partially connected wormholes. We can have wormholes with holes, handles, whatever. The point is we don't only get this contribution. And so in general, the path integral over manifolds will give us something different when we have multiple connected components from what we would get if we just took some power of the path integral. This has remarkable consequences that are very interesting when we are computing, say, von Neumann entropies. And in fact, the inclusion of these connected topologies is what allows us to recover the unitarity of the pitch curve in the Hawking radiation. This is a story by all of these people and lots of subsequent papers that I'm not citing here. The point is that these connected topologies is what allows us to recover sensible physical results. For example, when we compute von Neumann entropies. But what makes them even more interesting is that they also give rise to certain puzzles. And these puzzles are, for example, the factorization problem. The inclusion of connected topologies means that it no longer is so easy to make sense of the path integral, the Euclidean path integral, as a partition function. If we just have a bunch of copies of a boundary theory, there's no way for them to talk to each other. But again, the gravitational path integral, if we had those boundary conditions, would like to connect them somehow in the bulk. And this would lead to a lack of factorization. This is the behavior we expect from a purely field theory perspective. This is the behavior we seem to be getting from a gravitational path integral. So whatever it is that the gravitational path integral computes is not quite a partition function, or that's what it looks like. So I'm going to put some overline on top of it to denote this kind of uncertainty. And I'll remain agnostic as to what it is that we are really computing. There are some interpretations for what this overline means. Perhaps the most popular of them is that it means some ensemble average over theories. This can be made manifest in JT gravity, where we have some ensemble average over couplings of theories. But there are other possible interpretations of what this overline means. It could be that the gravitational path integral only computes self-averaging quantities. It could be that a non-perturbative completion would actually recover factorization. And then after all, the gravitational path integral really is just computing a partition function. I'll remain agnostic. I don't know what it is that we are computing. I'll just go ahead and compute things with the gravitational path integral and see what it means by seeing what results I'm getting by using it. Following the rules in the previous slide of integrating over geometries. And even though we get some interesting lessons from looking at von Neumann entropies, if we really want to take the gravitational path integral seriously, we could just go ahead and try to compute even more fundamental objects. And what is more fundamental in a theory than the generating functional? From the generating functional, you can compute entropies, but you can also compute correlation functions. So we'll be looking at the generating functional. If we consider the generating functional, we have two options of where to put the overline. We can put it on top of Z, as we were doing before. And then what we are computing is what is called an annealed quantity. We are basically just computing the gravitational path integral and then taking the logarithm. If we have some beta factors in front, we could call this a free energy. So this would be the annealed free energy. And in the ensemble averaging interpretation, this is the expression. Sorry? This is the precise expression we would be looking at. In the language of condenser theory, we would be integrating over couplings or letting the variables equilibrate and then computing the free energy. But we could also consider a quenched quantity. A quenched quantity is when we don't let the free variables equilibrate, but we take the free energy with the logarithm, and then we integrate over theories or over couplings. And that's what these overline logarithms here means. This is precisely what Engelhardt, Fischetti, and Maloney considered in JT gravity. And in particular, they considered this in gravitational theories. These objects have been considered in condensed matter for ages, but in gravity, we have not. And the first attempt at computing each of these separately in gravity was made by these three people. And what they found is, well, they had a very compelling argument for why this is the actual object that you should be looking at in quantum gravity and not this one. This argument is simply that is one of consistency with quantum theory. We are very used to such consistency arguments. We want unitarity, then we know we should include connected topologies to recover it. In this case, the argument is if you want that von Neumann entropies and Renyi entropies be identically zero for pure states or for full systems, then this is the object that recovers an identically zero answer in such cases. If you're actually handling this object, you only get 0 to leading order. That's not identically zero. It's not good enough at a fundamental level. So this is genuinely the object we should be considering. Now the question is, how do we actually compute this with a gravitational path integral? This side here is the ensemble averaging interpretation, but this is not something we can do in general in quantum gravity. With the path integral, we only have this side. So let me look at a simple mathematical identity. We can actually compute the logarithm using powers of the quantity inside. These equalities all hold so long as the limits exist. So let's assume they exist. And so what we have here is that we can compute the log of z by taking some limit over powers of z. And this is reminiscent of the usual replica trick that we use for the von Neumann entropy, except in this situation, I have the replica parameter m that tells me how many copies of z I have going to 0 rather than to 1. That's going to make this replica trick rather special. But okay, so we're handed this identity. Let's just put overlines everywhere. And that's how we get to the gravitational path integral and to a replica trick computation of log z. Importantly, we see that we are going to get wormhole contributions because now what we have here is a path integral over b to some power. So we have m boundaries. We're continuing that to m equals 0. And we saw that this object does contain connected topologies. So this is the way in which we are including the contribution of connected topologies into the generating function. This story could end here, but of course it doesn't because there's a subtlety, which is that continuing this m to 0 is not well defined in principle. Yes.
Just a notational question. When you say z to the m, do you mean z over one boundary to the power of m? Or,
I'm sorry, I cannot.
When you say z to the power of m,
yes,
in your formula, do you mean like a multi-boundary thing or like one boundary partition function to the power of like m of those?
So here,
the one above.
This one?
Yeah.
Oh, this is just, I'm just quoting the mathematical identity. Like this z could be x. At this point, I'm not considering anything gravitational or anything.
Oh, okay.
Yeah.
Right.
Okay, so the continuation is ill-defined in general, and in most cases, there's no Carlson's theorem here that you can invoke that guarantees uniqueness of the continuation given all integer powers. So we have to find some other mechanism that tells us how to do this computation. And so here's where the chef comes. This is just the, sorry. Yeah.
I just realized what my confusion.
Yeah.
So when you use that identity, how do you know this is not like m cop, like partition function of over one boundary to the power of m and not, why do you say it's over m disconnected boundaries and not one boundary to the power of m?
Yeah.
Which are not two equal?
I'm not sure.
You have made a choice in the last line, right? Because you said that could you go back one?
Yeah, once if you go back one slide. Yeah, over there you say they're not equal. The first line.
You mean that I've made a choice of picking one of these?
Yeah.
Yeah, you actually taken like the right hand side of the first equation with
Yes.
sorry, the left hand side of the
Yes.
left equation.
Yes, I'm literally understanding this expression as let me act with the gravitational path integral on everything. So it acts from outside. In that sense, I'm not really making a choice.
And if I put the m outside, like I compute p of b to the m
Yes.
outside, would I be computing the
Exactly. You get precisely this. So if you have the M outside, there's no funny continuation. You just have a power of a number. So you just get this. Yeah.
Okay. Yeah. You said the Carlson theorem's not applying. What goes wrong with the usual arguments that it would apply, like in standard replica tricks?
Well, I think one of the main problems in this continuation here is that we don't have a background space-time as a reference for m equals 0. In the usual von Neumann continuation, sorry, von Neumann computation, you're perturbing away from m equals 1. You know what the geometry looks like in m equals 1. It's just a perturbation away from it. Here we don't have that. You just get lost in the continuation. There's
Yeah, what happens specifically is when you try to analytically continue an M and you look at the asymptotic behavior of the function, it ends up being super exponential. So in, I think, imaginary direction. If you go in imaginary direction, it grows way too fast for Carlson's theorem to apply.
Yeah, so Carlson's theorem doesn't apply. And so in principle, there's no unique continuation in this situation. Is there any other question? Okay. Good. So what we're going to do in order to take control of this continuation is to go to a semi-classical limit. We're going to assume that higher topologies are parametrically suppressed by, say, in IDS-CFT, we'll take large n. In JT gravity, we are taking S0, go to infinity. So we don't have higher genus topologies. And in this limit, it's reasonable to expect that the kind of configurations that will dominate the path integral will be highly symmetric. So we are going to assume replica symmetry. And we are going to just look at saddle points. Once we have saddle points with replica symmetry, yes. Okay, once we go to replica symmetric saddle points, we can use the trick of Lukowitz-Nalvasina of taking a quotient by the replica symmetry group. This feedback. Sorry about that. And we can take the quotient, and what we get is a geometry which has certain conical defects, whose opening angle is parameterized by m. At this point, the meaning of m is not linked to the integers, so we can easily just continue m to the reals and handle the continuation on a saddle point, which is well defined. Yes, question.
So I think I've asked you this before, so either I don't remember your answer or I was unsatisfied with it.
I think I know the question.
The question is that the boundary computation has a full symmetric group symmetry here rather than just the cyclic group symmetry, whereas in Lefkowitz-Maldacena, the boundary computation has just the cyclic group symmetry.
Yes.
So I'm wondering how you are sort of justifying, it seems like an okay thing to do, but I'm wondering what your motivation is or how you're justifying restricting to cyclically symmetric saddles.
Yeah.
We're talking about cyclically symmetric saddles when the actual boundary calculation is a much bigger symmetry group.
Yeah, so the boundaries are just unique, are identical. So you of course have full symmetric group symmetry, which is a lot larger than just cyclic symmetry. When you fill in the bulk with geometries, for general M, you just don't have geometries with the with the symmetric group symmetry. You do have those for m equals 2, 3, and 4. You get a tetrahedron that does have that symmetry. For larger M, those just don't exist. You might consider geometries with higher symmetry than just the cyclic, but then it's a very M-dependent construction that would not lead you to any simple continuation in M. So yes, in principle, there's configurations which have larger symmetry than the cyclic, still smaller than the symmetric, But you wouldn't be able to handle that. So best you can do is cyclic symmetry.
Okay, so it would be accurate to say that you think that the cyclic subgroup of the full symmetric group is the largest subgroup that you can preserve in arbitrary party number.
That's fair.
Okay.
Yeah. Yes.
I have a small question and a small comment. The comment is that mic on? Yeah. Yeah.
Maybe that's the problem.
All right. And the question is just for the words annealed and quenched, why were those chosen? Like, is understanding that going to give me some intuition on how to picture these quantities? Is there any physical intuition behind the words annealed and quenched?
Probably a condensed matter physicist would say something more like clever than I could, and maybe you can.
I'm not a condensed matter physicist.
But you do know.
So Clifford Johnson has these lovely papers where he has studied the quenched free energy in the JT matrix model as well as GUE and related ensembles. And you know, these two things agree away from the spectral edge. Like if you look at sort of like quench versus the yield density of states. But the nice thing about the quenched one is that as you go to spectral edge, you can see sort of like, you know, first ground state, first excited state, second excited state is oscillations in the quenched density of states. That's one nice physical thing that comes out of this.
And well, I should say maybe one motivation for, or one distinction between these quantities in JT gravity in this paper by Sebastian, Netta, and Alex is that you see that the annealed free energy has a non-monotonicity at low temperatures, which gives you a negative thermodynamic entropy. That makes no sense. So the expectation is that by including connected topologies, what actually makes sense in gravity is to consider the quenched quantity, which you do expect will exhibit a monotonicity because you're basically just averaging over a bunch of free energies, all of which should be monotonic. Okay, so we can look at just quotient geometries, assuming replica symmetry. And so we can use the evaluation of the action in this quotient geometry to compute the action of the pre-quotient manifold, the full wormhole, by just multiplying. Replica symmetry guarantees that this works. And so what we get in a saddle point approximation is just an evaluation of the quenched logarithm, where we take the limit. Here we are doing the saddle point approximation. Here we are using the quotient geometry, and this is what we get. And we should think of this as the limit. M equals 0 doesn't make sense. So this is the limit m goes to 0 of our saddle points. You can compare this to what you get if you were doing, if you were taking the power outside, as I just said before. And in this case, what you would get out is just the evaluation of the action in the m equals 1 saddle point. So the difference between quenched and annealed can be seen at the level of which saddle dominates, whether it's the m equals 1 or the m equals 0. Now, you might wonder how sensible it is to include or to consider replica symmetry. And this goes a little bit perhaps in the direction of what John was mentioning, whether we can do better in terms of assumptions with symmetries. And so since m smaller than 1 is a rather unexplored territory, why would we expect replica symmetry? Or what does replica symmetry even mean, right? We have less than 1 copy. So we can ask Parisi, and Parisi would say, well, in spin glasses, actually replica symmetry breaking does occur, and it's important. You have to consider it. So let's try to incorporate some of these replica symmetry breaking in a one-step ansatz. We're going to do something very simple, which is to consider contributions which are neither fully disconnected nor fully connected, but something in between in a way that we can handle. So suppose we have 12 boundaries. We could consider configurations where we have them connected in clusters, say clusters of 4 boundaries. Each of the clusters replica symmetric within itself. and 3 copies of them to connect all the boundaries in some cluster. So we can consider some M1 number of boundary clusters divided in M, and then do the continuation with this kind of intermediate partially connected wormholes. And now we are going to analytically continue both M and M equals 1. Sorry, M1. M1 should be between 1 and M. And when we do the continuation, we're also going to allow for M1 to minimize the action. This is very reasonable here. We just want to pick the configuration which has least action. And when we do the continuation, what we get as M goes to 0 is another variable M1 here over which we are going to minimize. And the beautiful thing we see is that this prescription of one-step replica symmetry breaking recovers the 2 extreme cases that we had before, but also allows for, gives you an interpolation between them in the following sense. If M equals 1 minimizes the action, sorry, if M1 minimizes the action for M equals 0, then what we recover is a replica symmetric case. If it wants to take the value equals to 1, we recover the anneal result. But we have the freedom to pick some of the value between 0 and 1, which would give us an answer for the quenched logarithm that is replica symmetry breaking. Yes?
Are we taking the limit M goes to 0?
I've already taken that limit here.
So how come M1? Oh, I see. Between 1 and 2, we get the order switch. I see.
You might think, yeah, you might think that's a kind of fishy thing to do.
It's all we always do this.
This is what Paris did, and he got a Nobel Prize. So, yeah, that's how it works. So you should read this as M is between 1 and M, and in the continuation, that's how you deal with it. Yeah. You might say, okay, ultimately, what justifies this is whether we can do some computation where we check that this makes sense and we get a sensible answer. But until we have that computation available, this is the best we can.
So sorry, just to see if I get it right. You first send M to 0 and then extremize, or the other way around? Wait, your question.
Oh, sorry.
Yes.
Just to see if I get this, let me repeat the question. You first send M to 0 and then extremize, or the other way around?
The first one. Basically,
whoa,
this is what you would do also in this situation for M greater than 1. You first fix M, that's the number of boundaries for which you want to do computation. And then you ask which configuration dominates for that computation. Is it the fully disconnected, the fully connected, or something in between? So here you do exactly the same. Yeah. Okay. So here's the proposal. I don't know how I'm doing, but badly. Okay. Some general comments. So this prescription doesn't assume anything about the theory or the space-time dimensions. So up to this point is fully general. We just assume a semi-classical limit. The kind of geometries, these quotient geometries that I'm talking about can in general be modeled by codimension 2 branes, which generate the conical defects, which are of opening angle 2 pi over m, which can be tuned by the tension of the branes. M equals 1 is a very special place in this construction. And well, in general, it's the transition between positive and negative tensions, as you can see here. And what that means is that as we go to M smaller than 1, we're actually dealing with conical excesses rather than conical deficits. So for all the Renyi entropy computations, we are used to deficits. This is rather new. And if you want a more geometric picture of what happens near one of these defects, is the usual situation of a cone, the tip of a cone. You can model the Ricci scalar with some delta function if you include the point in the manifold. And the normal metric just looks like this, where, well, yeah, you get a tip of a cone, right? Now, if we look at 2 dimensions, we can be a bit more explicit. So I'm going to introduce a couple of ways of thinking about these geometries in 2 dimensions. And this toolkit is in principle valid for any M. So if you're doing wormhole computations for M larger than 1, say for any entropies or whatever, this will also work. In our case, at some point, we'll be taking the limit M goes to 0 or M goes to a half or something in between 0 and 1. But this is completely general. So let me remind you or give you some pictures of what this looks like in 2 dimensions. We're going to consider constant negative curvature manifolds, as in the case of JT. This picture might be familiar from the East Coast paper. If we have a replica symmetric wormhole, it will look like this, say for 3 boundaries. There's some modulus for these wormholes, which is the size of the throats. Here, I guess you cannot really see throats, but you can imagine these continues like a trumpet. And so the proper side of these throats is what is the modulus that we have over replica symmetric wormholes. When we take the quotient, what we get is basically one of these patches. And so these patch with these geodesics identified, this geodesic becomes this jagged line. The 2 fixed points of the replica symmetry become these 2 points. We have a conical defect of those points. The geodesic here becomes a smooth transition in the quotient. The modulus of the size of the throats becomes the proper separation between the defects. Might not be obvious here in the quotient, but this proper separation is actually bounded from below for M greater than 2. We'll see that later. So that's what the quotient will look like in general in 2 dimensions. So it's like a Poincare disk with 2 conical defects of opening angle 2 pi over M. And this is something I already said about the modulus. Okay, so I'm going to offer you 2 descriptions of this geometry, which are more useful, which might be more useful depending on what you want to do. The first one is a patchwise construction, where we are going to look at a fundamental domain where we can do things very explicitly. So I'm going to actually begin from the full 2-dimensional wormhole. And notice that we have a C2 symmetry that reflects the 2 fixed points. So we can actually slice this like a bagel, right? So if I slice it like a bagel, I can get 2 halves. One of the halves I can put in the Poincare disk. So this is just 1 half. The boundaries become these portions of the boundary. The geodesics connecting the boundaries become these geodesics, which are circles in the Poincare disk. B is for byte. It's like a byte of the disk. And 2 alpha parameterizes the size of this byte, which corresponds to the size of the throats in the wormhole. Now I can go from this half bagel to another smaller piece, which is just 1 mth, right? We have replica symmetry, so I can go to just a single patch by just cutting 1 portion here. And so in this patch, we can construct the quotient geometry by basically just identifying these lines. This creates the conical defect that we want. The geodesic portion, if we were to glue it to another copy, would recover the quotient geometry. So basically, this patch describes half of the quotient geometry very explicitly. Here, these, again, the proper distance between the defects, which you can see, I can go from a defect to the boundary, sorry, to the geodesic, and from the geodesic back to the defect in the other copy. So in this construction, we can just give all the ingredients. The metric we have is just the Poincare disk metric, nothing fancy here. With the identification in Z along these 2 lines. The geodesic bytes are just described by some circles. We have a simple relation between alpha and proper distance between the defects that is here. And you can see in the that obviously alpha cannot be too large. If it's too large, the geodesics will touch and the geometry will make no sense. This bound on alpha is a bound on D, which tell us that the proper distance between the defects is actually bounded from below. You might think, okay, this is a problem with the construction, it's just too simple, but no, it's just a fact about the wormholes. the way the wormholes trivialize is by the throats becoming of 0 size. But when the throats become of 0 size, there's still a non-zero proper distance between the fixed points. So the core of the wormhole is actually still exists and has the distance between the defects. Okay, so this is a fun fact about this simple construction. Why is this construction useful? Oh, wait, one more slide. What I showed makes sense for m greater than 1. If you go to m smaller than 1, you have a conical excess. You can no longer place this patch in just a Poincare disk. You need some covering of it, right? And so in general, for handling m smaller than 1, we're going to consider a multi-sheeted Riemann surface. And in the limit m goes to 0, you would consider an infinitely many multi-sheets, right? And that's fine. You just don't rub the circle here. This is useful if you have some model where everything reduces to local boundary dynamics, because you have everything explicit, the metric, the boundary conditions. And ultimately, all you need to impose is some conditions on the geodesic endpoints where your boundary dynamics are constrained in some way. And we did this for pure JT and for a model of JT with brains in the paper. You will see in the paper what we did if you read it. I'm not going to talk about it in the talk because I don't have time. But this model is not so useful if our theory doesn't reduce to just local boundary dynamics, because we would have to impose conditions along the full geodesic, and that's just not convenient. So in those cases, it's more desirable to construct some global chart that covers the full geometry. And so that's what we do next with the Baymax construction. Anyone knows who Baymax is? No teenagers here? Oh yeah, there's a teenager. This is Baymax. This is actually a picture of the face from Wikipedia, which is rather convenient because this really is what we're doing. Have an ellipse with 2 conical defects and some geodesic in between. So in the Baymax construction, what we do is we just treat the problem in terms of differential equations. We're going to start from a conformally flat ansatz, as we can always do for 2-dimensional geometries. So all we have to solve for is the conformal factor, or the Weil factor. The Weil factor in a geometry with 2 conical defects and constant negative curvature obeys this equation. This is just like a Liouville equation where curvature is constant, and these 2 delta functions incorporate the defects of strength given by m. I've chosen here to fix the defects at z equals plus and minus 1. We are in the complex plane. And it's convenient to go to elliptic coordinates. And then we have some chi, radial, phi. And in this useful coordinate chart, we can just place the boundary at some radial psi naught, because I'm fixing the defects at 2 points. The modulus is no longer the coordinate separation between them, but the eccentricity of the ellipse, which is given by the radial, the radius at which I'm placing the boundary. This replacement of the Weil factor allows me to simplify the problem a lot, because here I'm defining a new Weil factor where I've stripped away the boundary that I'm placing at the radius psi equals psi naught. And I'm also introducing this function, which we know explicitly, which basically consists of Green's functions that are and are also Dirichlet on the boundary. So basically, by introducing this new Weil factor, I'm solving already for the asymptotic divergence at the boundaries and also the defects. So I'm going to end up with some regular differential equation for sigma tilde. And this equation is this one. It might not look very simple, and it's not simple. We cannot solve it analytically, but we can easily look at it numerically, and we can solve it asymptotically, which is very important for JT dynamics. So asymptotically, we have a metric which looks like this. It has the boundary divergence, and it has some subleading metric term. This is in fact all we need if we want to evaluate anything in JT gravity. And we can actually find the exact phi dependence of this function asymptotically is given by some elliptic theta function. And all we leave, or all that we are left with as an unknown is some constant. Some constant that depends on the parameter of the theory, sorry, on the choice of eccentricity and on the choice of n. So this is a rather explicit solution of the asymptotic form of the metric in these geometries with defects. And this is going to be very useful in the next tale of two saddles for JT gravity, where we can evaluate things numerically using this metric. Okay, any questions before I jump into JT? Okay, so just some general equations in JT. Here's the action. For just pure JT, I'll then add matter because JT alone does not really accommodate saddle points. This is the JT part of the theory we're going to consider. In general, you can integrate out the dilaton, and that imposes the usual constant negative curvature. This term is topological. It gives us the Euler character of the manifold. This is what fixes the curvature. And this is the only dynamics that remain. They're given in the extrinsic curvature of the boundary. The way we preserve non-trivial dynamics in JT is with a specific choice of boundary conditions that work like this. We allow for a cutoff boundary that is dynamical. The way we do that is by imposing that the boundary lie at some level set of dilaton given by 1 over delta. And in the limit delta goes to 0, that we take the boundary to infinity. We instruct a fixed ratio between the proper length of the boundary and the value of the dilaton that is beta. And this beta is the inverse temperature when we consider thermal states. In order to simplify our computations, we're going to assume some C2 cross C2 symmetry. Let me play that again. That's the symmetry. Why? Because the underlying geometry does have that symmetry of reflections that fix the defects and reflections that exchange the defects. So for numerics, it's going to be useful to simplify the situation this way. So we're going to assume this C2 cross C2 symmetry. What we get in this two defect geometry is something like a Schwarzschild theory with extra terms. The Schwarzschild theory is what you get if you are in the disk or in the double trumpet. In our case, when we look at the dynamics of this boundary curve that I'm going to call the wiggle, when we look at the wiggle, we get the usual Schwarzschild plus another term, which depends on the promised subleading term of the metric. And here lies the dependence on M. So it's a sort of Schwarzschild theory with some self-interactions of the wiggle with itself or with the defects. You can do the sanity check, and for n equals 1 and 2, you indeed recover the Schwarzschild because G2 goes to -1/3. Here, I'm not explaining the notation very well, but this is the usual embedding of the wiggle in the circle. And yeah, question?
Yes. Sorry, so for general M, G2 is how to say you don't just have constant times phi prime squared?
It's not constant, it depends on phi.
So your bulk setup, you just have the two defects?
Yes.
And then claim is that with that, your asymptotics, you don't get, there's like these different versions of Schwarzian theory, diff S1 mod U1. You say you don't get one of those?
Oh, you mean the ones that actually have a constant?
Yeah.
No, unfortunately, you do get some dependence on phi.
Okay.
I
may ask you about that. Okay.
Yeah.
Thank you. Yeah.
Yeah. So it's a rather complicated Schwarzschild theory. It might be solvable, but yeah. And so in fact, well, yeah. If you take the equation of motion, say in this pure JT Schwarzschild theory, you get something like this, where you do get some non-trivial dependence on G2. Actually, this pure JT, at the level of the equations in motion, this one you can solve explicitly. And we did that, like analytically. But actually, you don't get stable saddles for any m other than m equals 1. So we consider adding matter. And that's what I'm going to talk about next, which is adding conformal matter so that we can try to stabilize wormholes, get some dominant wormhole, connected wormholes for general M, so that the computation of our quenched quantities is different from the annealed ones. Okay, so the kind of matter I'm going to add is very simple. It's just a free scalar, massless, as the action. And we are going to source it classically with some boundary profile. Here, this would be some boundary profile that we use to source the scalar field. And because the scalar is conformal, it's easy to solve or integrate the scalar over the bulk and leave it all as a boundary integral of some kernel against the boundary profile. This kernel S is known explicitly. You can think of it as a two-point function for the scalar. And so we have reduced the action of the scalar from a bulk integral to a boundary integral in the same way as we'd reduce the JT action to a boundary integral. So we can now deal with the theory as a purely boundary integral. And the equation of motion that we get for JT plus matter plus this scalar is an equation like this. This is a lot more non-trivial than what we had before, because this is an integral differential equation where we are solving for phi, but we have this integral. There's a non-trivial dependence between where the boundary lies and how we source the scalar. So we are not able to solve this analytically, but we can do some numerics, and that's what we did. So as a warm-up, we can try to see if our theory can stabilize wormholes for n equals 2, the double trumpet. And the answer turns out to be yes. So we can accommodate stable wormholes for n equals 2 by just sourcing the scalar with this very simple profile. This respects the symmetries we had before, but I don't think it's necessary here. Anyway, these plots are for these very simple profile. Here, the source is 0, so we don't have any saddles of the modulus. When I say stabilize the wormhole, I mean that the throat doesn't pinch off, which is what happens in pure JT. So we want the scalar to stabilize the wormhole throat. We don't have a stable saddle for the throat here. This is the modulus in the elliptic frame that I described before. As we increase the source amplitude, we see how it changes. This is the action, of course. And so we do get saddle points in the action, minima in particular, which stabilize the modulus as we tune up the amplitude of the scalar. The difference between dashed line and solid line here corresponds to a stability analysis. These are all solutions, but some of the solutions for the wiggle, but some of the solutions are not stable under perturbations away from the solution. These are unstable. These are actually stable. So these wiggle solutions are stable, and we are getting a minimum of the modulus. So these are genuine stable saddle points of the full theory. And importantly, if you just make J sufficiently large, it doesn't have to be too large, just comparable to S naught. These saddle points dominate over the disconnected phase of just 2 disks for the 2 copies. So these are actually dominant saddle points for the double trumpet. And that's very nice because it's not generally easy to get connected geometries to dominate in JT. But here's what we get. Now, what happens if we go to, or try to go to m smaller than 1, which is all we wanted to do throughout? we do find, again, saddle points which are dominant and stable as we go to m smaller than 1. So here is a little saddle we were proud of, which dominates and is stable. Here, there's a stable branch, the blue one, and an unstable branch, the red one. The stable branch has a minimum in the modulus, so it actually is stable. And it dominates with a smallest action for m equals close to 1/2. The bad news, or well, not necessarily bad news so far, is how these saddles don't continue below m equals 1/2. There's a very rich and complicated behavior of the JT action for m smaller than 1. This is something we've investigated a bit more exhaustively, but which I'm not gonna delve into much here. But there's a very complicated behavior of JT at values of m smaller than 1. And one of the things we observe is that all the branches of solutions we find for m smaller than 1 terminate at m equals 1/2. And at least numerically, it's very hard to find continuations of these branches for smaller m or new branches. So they seem to stop existing at m equals 1/2. Here we have the saddle I showed to you. And for m slightly smaller, these branches just go down without any saddles. So they seem to persist only up to m equals 1/2. So what's up with the overlying logarithm? What do we get for it as an answer if we consider these branches of solutions? Well, if we look at the action, what we see is that the action as a function of m keeps going down as we approach m equals 1/2. These are different values of the sources for amplitudes of the source. So top to bottom, we're decreasing the amplitude of the source. So we see for smaller amplitudes, the branch discontinues between n equals 1. It just doesn't exist here. And then exists for smaller m close to 1/2. So we have the action going down as we approach m equals 1/2. But we don't have anything here, at least not that we could find. So if we go ahead and look at our one-step replica symmetry breaking ansatz, sorry, let me mention one thing first. This is the action. We can actually make it as small as we like with the topological term, because for m smaller than 1, S0 is not a penalty. It's actually an enhancement of the action. So whenever saddles exist and are stable, we can always make them to dominate. So making S0 small, we can make these saddles dominate. And so they're going to participate in our computation of log z. And if we consider our replica symmetric ansatz with replica symmetry breaking, what we find, because they stop existing but minimize the action of m equals 1/2, is that the quench logarithm should be given by minus I of 1/2. So far, so good. So we can just look at what happens to the action, sorry, to the quench logarithm if we track these saddles. And this is where it was the best of saddles turns into it was the worst of saddles. The generating functional would be discontinuous if we track these saddles. And here's what I mean. This is the curve for the annealed generating functional. This is the curve for the quench generating functional if we track the 1/2 saddles. This is just, they exist all the way here. This is just because numerics get hard. But the point is, as we go to larger and larger values of the temperature, here's the plot of the free energy against temperature. If we go to larger values of the temperature, at some point we expect the quenched free energy to agree with the annealed one. In other words, we would expect this curve to join this one. But our saddles here don't want to do that. At some point, we will have a jump between this branch and this branch. It will go down eventually, but we will have a jump. There's a discontinuity. So there's obviously a, yeah. I didn't make an argument, and I should. So at high temperatures, the quantity, the free energy should be self-averaging, and you should expect that the quenched result just agrees with the annealed one. So it makes no difference when you take the ensemble average. And yeah, in general, you do observe this. And so here we have clearly a pathological behavior. There should be no such discontinuity. One reason that we might say, okay, this is what is going wrong, we might be missing saddles, right? This analysis was numerical. All we wanted to achieve here was a proof of principle that there exist saddles that can dominate and that would contribute to the quenched logarithm. Maybe we didn't find the saddle that actually gives you the correct answer, but we found existence of those. So you should take seriously that there are contributions beyond just the annealed saddles. There's another subtlety, and that's my last comment, which is one of stability. What I showed to you were saddles, and I was claiming that they are stable, but whether they're stable or not is actually a bit subtle. They are stable only if you consider perturbations which allow for a Lorentzian continuation. Let me explain it more. We were assuming some C2 cross C2 symmetry because it was simple for our numerics. There's another reason for why we would like one of the C2 symmetries to exist. And is that if we are performing some path integral that eventually corresponds to some Lorentzian variant theory, we should expect some existence of continuation to Lorentzian time that is real. And that requires a C2 symmetry. If you impose this C2 symmetry at the level of the configurations you integrate over, then the saddles I was showing to you are stable. So they should contribute to the path integral. Now, if I actually take the Euclidean path integral as a completely different object that doesn't care about Lorentzian time, and just consider all possible real Euclidean perturbations, then it turns out actually these saddles become unstable. So if I allow for perturbations that break this C2 symmetry, I do get, I destabilize the saddles. And so if these saddles become unstable, they no longer are genuine saddles to be included in a saddle point approximation. And in such cases, we would just conclude that we didn't actually find any stable saddles. So this gets to a very deep question about what are the rules of the gravitational path integral, in particular the Euclidean gravitational path integral. Does it care about whether Lorentzian continuations exist or does it not? And depending on that, we might get completely different answers to certain questions at the saddle point approximation level. Yeah.
In this case, the action in your setup, is the action bounded from below? So how, if it is, there must be a minimum someplace, right?
So it looks like that depends, for example, on which symmetries we impose.
But if you didn't consider imposing any, I mean, don't demand any symmetries.
I'm sorry.
If you didn't demand any symmetries, is the full Euclidean action bounded from below? If it is, there has to be a stable saddle somewhere.
Absolutely,
right?
I agree.
So maybe you're saying it's not bounded from below.
It clearly is for m equals 1, as we know for JT. It's not so easy to make an argument for m smaller than 1. So I would hope it is, of course, regardless of the symmetries we impose, but I'm not sure. And that depends on what actual form the action takes with this G2 factor.
I see. Okay, thanks.
So yeah, I would hope it is bounded from below without imposing any symmetries. And I would like to be able to have an argument to prove it, but.
Well, otherwise you must have some different contour Euclidean to start with. So
yeah.
Not stability.
Right.
You really need to.
Yeah, totally. Okay, so this is another possible objection to the computation we did, which has to do with Lorentzian versus Euclidean path integrals. And okay, so I'll just conclude with a summary of what we did. We provided a gravitational path integral replica trick for the generating functional in quantum gravity. It takes into account a one-step breaking of replica symmetry. We have some thorough toolkit of how to deal with these two-dimensional geometries with defects that can be applied for any M, really. It's not only for M smaller than 1 or anything. We constructed wormhole saddles for JT by just introducing classical sources for conformal matter. And the question about the stability of these saddles is one that is dependent on how we understand the rules of the Euclidean versus Lorentzian path integrals. If we impose the symmetry that allows for a Lorentzian continuation that is real, we get different answers for the two. We didn't find the actual answer for this one because our saddles gave us some pathology, but we did prove that there exist some saddles that gave you a different answer. If we allow for all real perturbations, then the two would seem to agree just because the saddles we find are unstable. It doesn't rule out that there are other stable saddles, real, actual global minima, that would give a different answer. But at the level of what we found, this would be the picture. And there remain lots of open questions. So you can read them in your free time and tell me what you find. I'll be very interested. Let me read a couple of them. So is there anything wrong with the saddle we found? Maybe that's not actually the dominant one. There's some other global minimum. Or maybe there's some exchange with other saddles that depends on temperature, or maybe it depends on going to M smaller than 1/2. That just gets tricky numerically, but maybe some better analysis would work. Our prescription for replica symmetry breaking is very simple and is the first step you take in, say, the Parisi ansatz. But the Parisi ansatz is a lot more sophisticated. Is there a version of the Parisi ansatz that we can implement in gravity and which would take general account of replica symmetry breaking? That'd be very nice. Then what are the rules for picking saddles? That has to do with what's the contour in quantum gravity and how seriously Lorentzian continuations or what role Lorentzian continuations play in genuinely Euclidean path integrals, and a bunch of others that you might be able to read or not, but I can show the slides if you're interested. Anyway, I'll end there. Thank you.
Thank you. Are there more questions?
Yeah, this question is just to reveal my ignorance about JT gravity. I mean, in higher dimensions, normally the Euclidean gravitational path integral is not bounded. I mean, the action is not bounded below. And you have to like rotate the conformal factor mode, and then you ask whether it's stable against other modes and all of that stuff. So what is the rule in JT around that? Is there negative conformal mode or?
For just pure JT, it is bounded from below. The solution to JT that is just that's a circle is the minimum.
I mean, I guess in 2 dimensions, the conformal mode is all you have for the gravity, right? What?
Sure, okay, yeah.
No, that's on shell, right?
In JT, it's exact.
I thought that was a consequence of the equation of motion.
Well, you can think of it as the equation of motion for the dilaton, but actually if you just rotate the dilaton and integrate over the imaginary axis, it's a proper delta function in the path integral that fixes r equals -2. So it's exact.
So after you integrate out the dilaton, right? But if we, it's not obvious that when we're asking questions about stability of Euclidean saddles, we should first integrate out the dilaton, right?
I would say at the full quantum level, the integral over the dilaton is what imposes the rigidity of the geometry to be constant negative curvature.
Right, I understand. So when you integrate out the dilaton, you get that condition,
Yes.
but it's not obvious to me that when you're asking questions about stability of Euclidean saddles, you should do it in the theory where you've already integrated out the dilaton.
I see.
Yeah, I understand you can integrate out the dilaton because the action is linear in it.
I mean, one way to think about this could be like, consider a metric configuration that is not r equals -2, which is the kind of thing you might be worried about, like in the configuration space for having a contributing unstably to the path integral. So fix such a geometry and then integrate the dilaton. The contribution from the path integral, the contribution to the path integral of that configuration goes to 0. So it's not necessarily that you need to, I guess there's like an order of maybe you want to integrate the dilaton first and then integrate the metric, or the other way around. Maybe there's a fixed order of limits you need to take.
I mean, I thought the question was, okay, we have a saddle, so that's actually solving the equations of motion, the classical equations. Now we're asking if I perturb it a little bit, what happens to the action and which perturbations are allowed. So I'm just saying maybe one should include perturbations.
But yeah, at the level of the perturbations I was considering, they're all perturbations with a non-zero weight, which would have a non-zero weight in the path integral. I guess these perturbations away from a rigid r-2 geometry would actually have a 0 weight, so they really do not contribute.
The thing that you're varying the stability
Maybe I didn't fully understand your question, but you integrate out the dilaton, but there are still things that you then vary in parameter space to study stability with respect to, like the wiggles, the boundary wiggles, and the modulus, which is just some other parameter that still exists even if you're not varying over possible dilaton configurations where r is not equal to -2. But I mean, you could ask what happens if you vary in your in like moduli space for configurations that don't satisfy that, but like you're varying the modulus and also the boundary wiggles while sticking with the level set where r is -2. But maybe your point is you have to leave that in order to get, in order to really properly understand like stability of the saddle. Is that what you were saying? Okay.
I mean, this is an instability in the boundary wiggles. This is not in the conformal factor. I mean, if you go back to like ordinary undergraduate classical physics, if you have a constrained system and you ask about stability, you just look at the variations in directions that satisfy the constraint. That's what we. So I don't think retaining the, how to say, in other words, the conformal factor is already frozen out here. If you talk about standard JT, there's you can integrate out dilaton, go to space of constant curvature metrics, go to boundary action, which is provably bounded below for standard scenarios, not apparently well, maybe the one that's going on here. I guess it's unclear. So there, yeah, it's a bit different. Something that, just a comment, I need to still ask you about this G2. If you study conical excesses in like the disk, or just like a single excess, and in that case you get a Schwartzian theory that is sort of related to the ones that diff S1 mod U1, but there the boundary action is not bounded below. Like it is bounded below for m equals 1, but I mean, if for any m that's less than 1, it's not bounded below in that case.
Okay,
So
good.
just a comment, yeah.
Well, that's suggestive. here.
Yeah, you can find configurations. I mean, at M into at M, well, and also at M1/2, what's special about that? That's where now you have 4 pi angle in the bulk, right? As you go around your deficits. In that case, there's some funny interplay between like Schwartzian theory and then something in one higher dimension that produces characters of Virasoro algebra.
Okay.
In that case, the Virasoro character that you get is a degenerate character. There's some funny things that happen as you adjust M to that value.
And so this is specific to M equals 1/2.
This is specific, yeah, well, at M equals 1 over integer, 1 over 1/2, 1/3, 1/4.
Okay, good. I mean, one of the reach things we observe is that there are singularities occurring at every M equals 1 over integer already at this level. So I guess
this is if you have a single, I'm not sure if there's a relation to what you're doing or not. If you have
oh,
a
so in
single
our
defect-
case with 2 defects, we also have this pattern that at every M equals 1 over integer, we get some like repeated structure or like fractal. So maybe the situation with just a single defect is not that different, or there's some relation to this one. Okay, that'd be interesting to see.
Okay, good. Thank you very much again.
Okay.